Hello, welcome to another episode of Mystery Science. I'm Mr. E, and today I'm going to be taking you inside the atom. If you haven't seen the rest of this playlist, please have a quick look, and I really do recommend watching this as a playlist and watching it all the way through. So today's lesson, we're going inside the atom. We're going to be looking at isotopes. What on earth are those, Mr. E? Why are you talking to me with your weird language? Well, let's find out. This lesson, we're going to be able to state what an isotope is. That's quite handy. It's a weird word, and we'll find out what it means in a minute. We're also going to be able to represent them using symbols, but you need to know what they are first, so we'll get on with that in a minute. We need to explain how atoms of different elements are different. If we look at a periodic table and we look at all of the elements on there, what makes oxygen oxygen? Why isn't carbon the same as oxygen? Why are they different? And we'll look at that. We're going to look at the masses and charges of the three subatomic particles. We've just done that in the last lesson. So if you haven't seen that video already, skip back and watch that. And as I say, watch it as a playlist. You won't miss a thing. Subscribe to the channel and you'll see when the next ones come up as well. We're also going to have a look at and understand why atoms themselves have no overall charge. Atoms are always neutral. So here we go. Picking up from our last lesson, this is our current understanding of the atom. And I say current understanding because atomic models change. When we get new technology and we're able to explore new things and find out more about them. So let's imagine the successor to the Large Hadron Collider at CERN all of a sudden finds out a new fact about atoms. We have to completely change the way we think about them. This model goes out the window. Off it goes, and we teach your grandchildren a completely different set of atoms and atomic rules to the ones you're learning right now. But that's simply how science is, and you can choose later in life whether to follow these developments or not. It's completely up to you. We have these very, very tiny negatively charged electrons on the outside of the atom. And then we have the positive guys, yay! Positive protons in the nucleus of the atom. And then we have the neutrons. The neutrons have no charge. They basically don't interact with anything, but they do hold the atom together. They're so dull, in fact, that when a neutron walks into a bar, it says to the barman, "Hey, barman, I'll have a pint of Coke, please. How much is that?" And the barman says, "For you, neutron, no charge." Okay, now if you're one of my students, you'll be used to that kind of rubbish. In fact, you've probably heard that joke about 600 times before. But if you're not, and you're new to Mystery Science, then hey, welcome aboard. Let's take a step back for a moment and let's define a few words. Nucleons! Now I've said nucleus a number of times in the last 3 videos, but I haven't said the word nucleon, and if I have, I've slipped it in without noticing. But a nucleon is any particle that exists inside a nucleus. That's neutrons and protons. Electrons are negatively charged tiny particles with completely irrelevant mass that float around outside of the atom. And in fact, I've told you that atomic models change, and we kind of actually know that what I'm telling you already isn't really true. But what we do know, at the moment at least, is that electrons are really tiny and electrons can't be broken down into anything else. But then that's what Dalton said about 400 years ago. So we could be wrong. And that's the great thing about science, is that the things I'm telling you now, you are going to be learning in about 20 years and coming up and saying, Mr. Radioactivity, you were completely wrong. Look, this thing is this. And I'll go, ooh, that's very interesting. And then eventually it'll work its way down to the syllabus and I'll be teaching it. And I'll go, I remember when the guy that invented this came up to me, so I used to teach him science. That's going to be one of you lot. Protons. Protons are positively charged particles that sit in the nucleus. Therefore, they are a nucleon. So a proton is a nucleon. It sits in the nucleus. The nucleus is the body of nucleons, the center of an atom. A neutron, neutral particle, doesn't interact with anything, but is also a nucleon, sits inside the nucleus. An atom is a neutral particle. An atom has no overall charge. It has exactly the same number of protons as electrons. This is a law of the universe. Now, atoms do, and I'm going to tell you about them losing electrons and gaining electrons. And you've probably heard in chemistry about atoms losing, gaining, and sharing electrons. So that you're now saying, well, Mr. Rowley, what you've just said is not true, but it is. An atom is always neutral. If it's not neutral, if it doesn't have the same number of electrons and protons, it's not actually an atom anymore. We call it something else. So an atom is always neutral. Same number of protons as electrons. Got 6 protons, you've got 6 electrons. Got 8 protons, 8 electrons. I could do this all day, but that would be boring and you'd unsubscribe from my channel and I would cry. So let's have a look now at a few more definitions. Alright, Mr. E, stop with the definitions. Don't worry, there's only 2 more and I'll show you a little pretty picture straight afterwards. The first one is this, atomic number, also known as proton number. This tells you how many protons and therefore how many electrons are in an atom. Carbon, for example, has the atomic number of 6. It has 6 protons and 6 electrons. The mass number. The mass number is the number of nucleons in an atom. So, carbon has 6 protons and 6 neutrons in its nucleus. It has 12 nucleons, and therefore its mass number is 12. Shock, horror. And you'll see this on the periodic table. You'll see a big number, that's the mass number. A small number, that's the atomic number. The atomic number tells you how many protons there are in that atom. You'll see that the way it's represented is the same as on the periodic table. There's the chemical symbol, C, that's carbon. Then you have a small number, 6, and then you have the mass number, the bigger number, 12. I would dearly love to be able to say to you that they all look like this, that the mass number is at the top and the atomic number is at the bottom. And you will always see this in the periodic table, and you'll pick up a periodic table and go, aha, top number must be the mass number, bottom number, atomic number. But no, because some people print their periodic tables the wrong way round, and unfortunately there's no actual standard. The one I'm actually telling you is possibly the wrong way round. There's probably chemists writing hate mail right now going, no, the atomic number surely should be at the top, obviously the mass number at the bottom. But unfortunately for you guys, there just is no standard. It's one way or the other. So you have to remember the largest number is the mass number. Smallest number is the atomic number. What makes elements different? Why is oxygen oxygen and carbon carbon? Here is a hydrogen atom. Hydrogen is really dull, but also quite fascinating. It is simply a proton surrounded by 1 electron. Same number of protons as electrons, 1 on 1. So you have this one teeny tiny electron buzzing around 1 proton. Wow. But this is helium. Now we have 2 protons. And we've also got 2 neutrons surrounded by 2 electrons. So now in the hydrogen we had a mass number of 1 and a proton number, an atomic number of 1. Here we have an atomic number of 2 because there are 2 protons, and a mass number of 4. I've nearly got the wrong number of fingers. And a mass number of 4 because there are 2 protons and 2 neutrons. There are 4 nucleons. And here is carbon. I've spoken to you about carbon before. Carbon has 6 protons and 6 neutrons. Therefore, it has a mass number of 12. But what's making carbon instead of helium and hydrogen? Now, I'm telling you some things as facts, so hopefully maybe you can start to deduce what the actual thing I'm trying to get at is. Here is some oxygen. It's got 8 protons, and this one's also got 8 neutrons. So its mass number is 16. Now, we don't always have the same number of neutrons and protons. Sometimes there are more neutrons than protons. What I'm trying to show you is that all of these have a different number of protons. Carbon always has 6. Oxygen always has 8. Hydrogen always has 1. Helium always has 2. The proton number, the atomic number, tells you how many protons there are in that atom. That atom has a specific number of protons. Each element is that element because of that number of protons. If you were to take a piece of carbon which has 6 protons in it and somehow magically stuff 2 more protons into it, so now it's got 8, it's not carbon anymore, it's oxygen because it's got 8 protons. That's what makes these elements different. It's the number of protons that exist in the atomic nucleus. So carbon, no matter what type of carbon you have, whether it be diamond or graphite or a nanotube or a buckyball, these are all things made of carbon. They're all things that you will find as allotropes of carbon in chemistry, but they've all got 6 protons in the nucleus. Oxygen, no matter where you find it, always has 8 protons in its nucleus. That's what makes it oxygen. So here now, I have 3 different types of carbon. They're all carbon atoms. If you look at this and count the number of protons, you will find there's always 6 protons in the center of all of these. Consequently, there are 6 electrons on the outside of each of them. So they're all carbon. So what's different about them? Well, the first one has got 6 neutrons. The second one has 7 neutrons. And the third one has 8 neutrons. So we have the same number of protons, so they're all carbon, but they have a completely different number of neutrons. Now these are all 3 naturally occurring types of carbon. The first one we call carbon 12 because it's got 12 nucleons in it. 6 protons, 6 neutrons. The second one has 6 protons, 7 neutrons, so therefore 13 nucleons, and we call it carbon 13. The third one, we have 6 protons and 8 neutrons, giving you 14 nucleons, and we call it, you've guessed it, carbon 14. Why is this important? Well, if you have a look, it actually shows you that carbon 12 is stable. And in fact, not only is it stable, it's incredibly common. It's the building block of life. It's the Lego block of all organic things. Plants are made of carbon. We are made of carbon. Anything that is alive is carbon-based. There's carbon everywhere. Without the carbon, we simply wouldn't exist. Carbon 13, on the other hand, it's natural and you'll find it all over the place. It's stable, but just not as much. Carbon 14, however, is unstable. It's radioactive. It will, at any given point, sit there going, I've got too many neutrons. I've got too many neutrons. Nope, nope, bah! And it will break apart. And actually, when it does that, it will lose a proton and some other stuff, and it'll stop being carbon. It'll turn into something else. And that is the essence of radioactivity. That is nuclear physics. And that is what we're going to be focusing on for this part of the course. So this carbon-14 does exist in nature, and in fact 1% of all organic life is made of carbon-14. Now, because carbon-14 is radioactive, and we know that it decays over a certain period of time, when something dies, the amount of carbon-12 and carbon-13 in the body stays exactly the same. The amount of carbon-14, though, gets less, because as the carbon-14 decays, becomes unstable, just breaks apart randomly. This process is happening all the time. But normally, as we are losing carbon-14 through radioactive decay, yes, we are radioactive to some degree. What we're doing is they're then ingesting some more carbon-14 somehow, either in the food we eat or in the air that we breathe. We're getting more carbon-14, so it roughly balances. But when we die, that balance isn't maintained. Once we're dead, the amount of carbon-14 goes down. And so scientists can actually find out how much carbon-12, 13 and 14 there is in a sample of tissue and use that to find out roughly how old something is. And this is called carbon dating. I recommend doing a little bit of reading around that. You could be asked questions on it. Just to further illustrate this point, here are 3 isotopes. I forgot to mention that those 3 types of carbon are called isotopes. Now, here's 3 isotopes of hydrogen. Hydrogen normally, most abundant element in the universe, is 1 proton with 1 electron orbiting around it. But you can have a neutron here somewhere, and this is called deuterium. And deuterium, all of a sudden, now you've got a different mass number. Your atomic number of hydrogen is still the same. It's still 1. There's only 1 proton. But now you've got a neutron as well. So you've got 2 nucleons. So you've got hydrogen 2. But you've also got tritium, where you've got 2 neutrons. Because it's 2 neutrons, you've now got 3 nucleons. 1 proton, 2 neutrons. That makes the 3 in tritium. So now you've got an atomic number still of 1, because it's got 1 proton, but a mass number of 3. Now this is called an isotope. It's the same element, but it has a different number of nucleons, different number of neutrons. So here's the definition of an isotope. An isotope, very simply, is a different form of the same element. It's just got a different number of neutrons, but it's always got the same number of protons. Otherwise, it's a different element. Carbon is still carbon when it has 6 protons in it. Carbon-12, carbon-13, carbon-14, they're all carbon. They've all got 6 protons. They have 6, 7 or 8 neutrons, and that makes them isotopes. It's the same number of protons, but a different number of neutrons. What have we learned today? Inside the atom, we've had now a definition for what an isotope is. It's the same number of protons with a different number of neutrons. We've seen how to represent these using symbols. We simply change the mass number of the on the chemical symbol. I've explained that changing the number of protons changes what the element is and how the element interacts with the universe. And I've also talked about the masses, or the relative masses, of the small subatomic particles. And I've told you that protons and electrons in an atom are always the same, meaning an atom has no overall charge. It's always neutral. I hope you join me next time for a look at electrons and orbits. It's a pretty cool one because it shows you how we make things like neon signs and other cool stuff. And it's one of my favorite things to teach when it gets to A level because it gets really, really pretty. So click on the link for the next video, have a look at the playlist, and subscribe to the channel so you will be updated as and when these videos released. And if you're bored and don't want to learn any more physics for the time being, do come back, but also feel free to watch me open some Pokemon on my other channel. Stay safe and we'll see you soon.